Hello, in this video I'm going to take a first look at lenses. So these are things for focusing or dispersing a beam of light via refraction. And when I say beam of light, I mean you can have microwave lenses, acoustic lenses, all of these other things, but typically particularly when we're starting out, we're thinking about light being refracted by glass in order to converge, diverge, depending on what our needs are. So what's exactly going on with all of this? How are we engineering these things in order to manipulate light to our advantage? Right, well, single lenses, they're categorized by surface shape. So you can have convex surfaces which curve outwards. You can have concave surfaces which curve inwards. So this is in terms of the direction that the light's coming in. And then you can have flat surfaces, planar surfaces, where they're flat, and we're combining these in a whole load of different ways. So I'll just look at a few of the basic designs that you can have on these. I mean, you've got the converging lenses. So these are the ones which are built around convex surfaces, and these surfaces are usually spherical surfaces. So they're parts of the surface of a sphere. Now, I know we've spoken about before how parabolic surfaces are better at focusing and reflecting and things like that, and getting stuff focused to a point, but the parabolic surfaces on lenses are a lot harder to actually manufacture. So most of these surfaces are going to be spherical surfaces. Now that can introduce a few problems, but I'll deal with those later on because they can be mitigated. So let's think what's happening with a convex surface. So if we've got our convex surface, such as this, and you get some light coming in, so say it comes in at a fairly parallel, so a horizontal line of light. So our normal to the surface is like this. This is our angle of incidence, and we know we're going to refract towards the normal because we're going from air to glass, and glass has got the higher refractive index. So that means we're going to be refracting downwards. And that's why this convex surface is going to be focusing the light. It's converging the light. It's what's called a positive lens. So we can, we might have, well, maybe two convex surfaces. So again, when we get to this second refraction point over here, again, we've got another normal. That's now our angle of incidence, and we're going to refract away from the normal when we come out into the air. So again, it's going to curve it down. So we've got this converging approach from what's called here a biconvex lens. And we can describe these surfaces in a number of ways, and the lens as a whole in a number of ways. But perhaps the key ones are you've got the radius of curvature for each surface of the lens, so radius of curvature. So if you think of these, well, these are spherical surfaces. So if you continued it all the way around and you actually turned each surface into a whole sphere, that sphere would have a radius associated with it. So taking this one surface, well, what would the radius be? That distance is going to be, so for the first surface, let's call it R1. That is our radius of curvature for that surface, that convex surface. And that's got a value that we can assign to it, saying, well, how curved it is. The more curved it is, we're going to get more refraction going on. We're going to get more bending of the light. So because we're measuring the radius of curvature off to the right, then we'll say that's greater than 0. For this second surface, well, the radius of curvature is going to be off to the left. So our R2 we'll say is less than 0. So that's how we can describe those surfaces. We can also describe the lens in terms of the focal length. So our focal length, which is denoted with a letter F, and that will be the distance from the lens that we've brought the light into focus. So that is some distance there. So that's telling us something about the converging power of this lens, which clearly is going to be related to the radius of curvature of each surface, because the more you're curving these surfaces, the more it's refracting the light, and the shorter the focal length is going to be in this particular case. So you get this in the, well, what's called the thin lens approximation. I think this is the, they call it a lens maker's equation, I think it is, or something like that. So you get this lens maker's equation where you can say 1 over the focal length is roughly equal to something to do with a refractive index in a material. So refractive index minus 1 times 1 over R1 minus 1 over R2. Remembering that R2 is going to be negative in this particular case. So that's giving us something to do with the focal length, or the reciprocal of the focal length. And that is going to be reflected in the optical power. So the optical power is this 1 over the focal length. So that's telling us something to do with magnification. Now, magnification is a tricky thing when it comes to lenses, and I'm going to talk about magnification a lot more in the section on eyepieces for telescopes. And we can look at these lenses in the eyepiece plus the telescope being a whole system and trying to work out what we mean by magnification, because it's not as simple as it could be. There's some complexities to it concerning field of view, how big does the object seem to be, and then how big does it seem to be within the field of view. So there's some complications around magnification that I'll put in a separate video for that reason. But we've got these ways of describing a lens though: the focal length, radius of curvature of each surface. So these are important features. Now, I mean, 3 other simple lens structures that we could have. I mean, we could change one of these surfaces to be a flat surface. So we'd have a plano convex lens in this case. Why would you want one rather than the other? I mean, this one on the left here, this is typical that you'd see in a magnifying glass. This is better if you've got objects that are situated quite close to the lens. So if you're looking at something that's nearby, it's better to have a biconvex lens. I mean, this is why if you've got someone who's long-sighted, they will have a biconvex lens in their glasses to help them look at things which are close up. So they're better for looking at things that are close by. Having a flat surface, this is better. You'll see these more in telescope eyepieces where we've got parallel light coming in, rather than, you know, if you've got something which is close by, you don't have parallel light coming in, the rays from the object are, you know, spreading over an angle. So if you've got parallel light coming in because you're looking at something like a star which is really, really far away, then this is going to be a better option for focusing your focusing your light. So yeah, we've got those setups then for these converging lenses. You've got the opposite, the diverging lenses. So you can have a biconcave lens. So these are ones where we're now refracting the other way. So as we come in, it's going to refract away, and then it's going to refract away again. So we're diverging our light away from being parallel. And this is useful. I mean, we saw biconvex is good for people who are long-sighted. Well, this is good for people who are short-sighted. So, you know, if you're short-sighted, if we're thinking about those two conditions in terms of the eye, you've got light coming into the eye and it's being focused. You want to focus it on the retina. Well, if you're short-sighted, it's being focused short of the retina. If you're long-sighted, it's being focused past the retina. So you want something that's either going to bring your focal length in, which is what happens with these converging lenses. You're shortening the focal length. Or if you're short-sighted, you want to push your focal length out to get it onto the retina. So that's what's going on there. These are lengthening your focal length. And we can describe these surfaces in the same way. And then, of course, you can have another one which has got a concave surface and a flat surface. I mean, you've got all manner of other ones. You've got the meniscus lenses as well, where you'll have, you know, 2 of them going in the same direction, which are, yeah, these are a bit more sort of fiddly. These could be used for, you can have ones which are wider in the middle, which would be your converging ones, and ones which are narrower in the middle than at the edges. These are good for correcting spherical aberrations and things like that. but don't worry about those ones too much here. I mean, these 4 are the ones that come up most often, and these get combined together into compound lenses. You know, a lot of the stuff we're going to look at for eyepieces for telescopes, you might have a biconvex lens which is stuck onto a plano concave lens in order to create this doublet lens, and this can be useful in various ways, for correcting various aberrations, little errors and things that creep into the lens design, because they're spherical or because they're going to refract to the different frequencies of light by different amounts. So either of those effects, I'll do a separate video on aberrations, either of those effects means you're going to get different focal points depending on frequency of light or whereabouts on the lens the light is hitting. So we don't really want those. It's creating a blurred image, so we want ways of correcting them, and quite often these doublet lenses are going to be doing that. So that's just a quick overview of some of the terminology around lenses and some of the basic types. As I say, I'll look at some of these in more detail in telescope eyepieces, aberrations, and whatever the other thing was. Oh yeah, getting on to looking to things of field of view and magnification in subsequent videos, because I don't want to try and get everything in here. It will just go on for days and get too confusing. So, but from here, just take the idea that we've got these different surfaces. You can combine the different surfaces in different ways. If you've got convex surfaces, you're converging light. If you've got concave surfaces, you're diverging light. And the focal length of the lens is the thing which is telling us something about the optical power of the lens and how strongly it's converging or diverging light. So that's your main sort of set of takeaways from this video.